All right, guys. We're now in chapter 6, and we want to be talking about another ideal basic circuit element called the inductor. The inductor itself is going to be interesting in the sense that we will see that the IV characteristics for the inductor are no longer algebraic equations like they are for a resistor with Ohm's law, but they are actually going to be either differential equations or integral equations. We really want to explore this. But before we do that, let's talk about some fundamental ideas that underlie how inductors work. So this is a section on the inductor. Now, the model that we have for the inductor is the following. We have, and I'm going to try to draw this as carefully as I possibly can. Here what we actually have is a ferromagnetic iron core. Ferromagnetic core. This is usually iron. Now, this kind of toroid force kind of thing has a certain cross-sectional area. That's going to be cross-sectional area A, and it's going to be the same all the way around, right? So hopefully you can convince yourself that it's all the way around, even though it's not like that in the picture. And what we're going to do is we're actually going to take a piece of wire and we're actually going to wrap it around this ferromagnetic core. Now, keep in mind that I'm going to exaggerate all of the spacing on the wire, but the spacing itself is going to be for a realistic inductor. It's actually going to be such that there's really kind of like no spacing or no gaps in between. This is just for the clarity of the drawing. So here's suppose that I start with a terminal here. It starts with a wire and then it wraps around the entire structure in such a way that it looks kind of like this. And I'm going to keep on wrapping it and wrapping it until I wrapped it all the way around. Right? And there's a certain number of turns as we actually move around. So this is going to have a total of M turns. Right? Now, one of the things that I can actually do is, given the wrapping of this, I can actually feed in current into this. Suppose that I feed in the current into this in green like this. This current itself is actually going to flow through the wrappings, right, coming from the back side through the front side, and so on and so forth, as it actually moves all the way around that wire. And hopefully one of the things that you guys ended up learning way back in the day was that currents themselves, what they do is they generate magnetic fields. So currents, I generate fields, magnetic fields. Keep in mind that in the language of electrical engineering, they tend to call this the magnetic flux. Right? So I'm using the term magnetic field. This is a physics term. In electrical engineering, they use magnetic flux or just flux for this. Right? Either way, this is what ends up happening. And the direction of the magnetic field generated here is given by what they call the right hand. Right hand rule tells you that if you actually place your thumb in the direction of the current, you wrap your fingers around until you actually hit where the magnetic field is trying to be found. Your palm is going to be perpendicular, and it's going to be in the direction of the magnetic field. So here you have to think about this in 3 dimensions. So suppose that you actually have the it's actually wrapping around the back, and you want to find the magnetic field. Also, one of the things that you can kind of as you picture this is that inside of this very magnetic core, you're actually going to end up with a field that wraps around the core like this, right? So I am I am drawing these vectors as if they were kind of curved arrows. But one of the things that you can actually convince yourself as you actually go through is that if we're looking on the inside of this inductor, like this set of coils, the magnetic field is going to be in the direction as stated there. Right. Now, one of the reasons this is important is the magnetic field itself is actually penetrating through the surface area of the coils. And this leads to a new quantity, a physical quantity that physicists call the magnetic flux. In the language of electrical engineering, this is the flux, what they call the flux linkage, right? Magnetic flux, this is kind of a definition, is denoted in physics like this. It's in its simplest form, the simplest equation, it's a measure of how much of that magnetic field is penetrating through the surface area of the coils themselves. And in this particular case, notice that we had mentioned that the coil itself, right, as they're are tightly round with the cross-sectional area A. And if B is the magnitude of the magnetic field, then the total magnetic flux going through one section of the coils is B times A. Right? Now, keep in mind that this is the simplest one. If you really, really wanted to get technical, this itself would be an integral. It would be the integral of the magnetic field times the differential cross-sectional area for the actual surface. And if you happen to have a total number of n currents, like this, then the total flux here is n times the flux going through each one of those little sections. Now, the reason this is important, right, is notice that the magnetic flux here is proportional. And this is the important part. It is proportional to the magnetic field. And hopefully one of the things that you should have learned in physics is that the magnetic field is proportional to the current that's actually flowing through your coils. So let's write down what the relationship here is. So here we actually have the magnetic flux is proportional to the magnetic field. The magnetic field is proportional to the current, right? And this is where the kind of kicker is. Since the magnetic flux is proportional to the magnetic field and the magnetic field is proportional to the current, the magnetic flux is also proportional with the current. And the constant of proportionality between the magnetic flux and the current is what we call the inductance. So let's actually write that down. The proportionality constant between the magnetic flux and the current that generates it is the inductance. And we use the letter L, the inductance. So in equation form, magnetic flux is equal to the inductance times the current, like this. Let's talk a little bit about inductance. Inductance itself also has units. The units of inductance are volts times seconds to amps. This also has another more abbreviated common name. This is the Henry, and we use the capital H to denote this. Now, in the next video, one of the things that we're actually going to do is we're actually going to take this and we will derive the IV characteristics for an inductor using this relationship and one last other relationship, another law of physics called Faraday's law of electromagnetic induction. But we'll see that in the next video.